Now that we've talked about precision and accuracy, we're also going to need a way to represent that when we write a number. So the reason for this is, like you may remember from the introduction video on making my pot of spaghetti. If I just dump some salt in the water, that is not the same thing as if I was baking bread and I ended up measuring my mass to exactly the nearest 10th gram. So I need a way to represent this. To do this, we're going to use something called a significant figure. So they're the way we write numbers to inform others about how well a particular measurement is made. So what does this mean? So when I take a scale, and I've got it and I have a little object on it. Let's say that little object weighs 3.0 grams. So when I write this down, this is how well I know it. I don't know anything about any of the digits the scale doesn't tell me. The real weight could be 2.96 grams. That's because the 6 would round up. It could also be 3.04 grams. Both of these, the scale would tell me was 3 grams. That's because the scale has an accuracy limit. It's only made to measure things so well. So it's not going to report other numbers that it doesn't know. Now some things aren't like scales. Some things you're going to measure. So let's take a ruler as an example. This is going to be a tiny ruler. It measures in centimeters and only has 4 marks. 1, 2, 3, 4. And these are all centimeters. And let's say we've got a line that comes through right here. And obviously I'm drawing poorly. This is kind of a crooked thing. Now when I see that, it's closest to the 2. But I know it's not exactly 2. So when I write it down, when you have an instrument like a scale or a thermometer that doesn't report digitally, you're going to estimate one of the digits. So I'm going to say that's, let's call it 2.2 centimeters. Now you might not agree with me. You might think it's 2.3 or 2.1 or 2.4, and that's okay. So when we report our number, we're reporting however many numbers we know. So I know the 2 exactly. Then the last digit is going to be an estimate. This is the one we know kind of. Because I know it could be 2.2, but it could also be 2.3 or 2.1. But I don't think if every student in the class took this ruler and saw that measurement, unless you misread your ruler, you're not going to say it's 3.2. You're not going to say it's 1.2. You're going to say it's 2 point something. And probably something close in the lower numbers, you're probably not going to say that's 2.9. It's not nearly as close to the 3. So when we report these, we're estimating the last digit. So now, we need a way to keep track of this. So when I read a number, if it's significant, that means it's one that I knew something about the measurement for. If it's insignificant, that doesn't contribute to how well I know the number. And this is something we'll work on over time. If it's a little confusing now, we will keep working with it. So first we'll start with the easy ones. Anytime you see a number, if it's not a 0, it's significant. So the number 123 has 3 digits. None of those are zeros. They're significant, that means. 95,874, 5 digits. Those are all significant. I have the number 24. That has 2 significant figures. Both of them are non-zero. Every other rule from now on is about how to deal with zeros. They're the ones that do weird things because sometimes they're just there to help us know where the number is, like to place a decimal point, and sometimes they're part of the measurement. So we have to have rules to describe that. And it affects how we do math later because you're not just going to use this measurement by itself. You're going to convert it into something else. Maybe you're going to use your ruler and you're going to measure a block and you're going to find its volume. In some way, you're going to transform it. So this number, while right now it might seem like, why do I care about a significant figure? It's going to help us do math later and keep that accuracy. How does me knowing the ruler at 2.2 affect the volume of a cube I measured with that ruler? So that's why we keep up with this. So, next rule. Leading zeros are going to be any zeros that occur before the first non-zero number. They are never significant, and they only serve to locate the decimal point. I'm not getting to say that, because in chemistry, I almost never get to say never. I'm usually like, almost always. There's one exception we're not going to teach you, but it's there. But this one I can actually say never. So this number, 0.0001, those first 3 zeros and this 0 before the decimal, none of those count. Only the 1 does. That's 1 sig fig. This 0.0023, none of those zeros count. That's 2 sig figs. 0.0247, 5, that's going to be 4 sig figs. The ones before the zeros up here don't count. Next, we have what are called interior zeros. This is when they occur between 2 significant figures. So for example, here we have the number 102. This 1 and this 2 are significant. The 0 occurs in between them. Therefore, it's significant as well. That's what makes this 3 sig figs. 3,405.01, both of these zeros occur between other numbers that are significant. Therefore, it's 6 sig figs. If I had 2.07, That 0 is between the 2 and the 7. Therefore, it is 3 sig figs. Please note, you do not need to memorize these names. I tell them to you so that way we have something we can talk with. Maybe it helps you to remember them. But if you don't know that it's a leading 0, you just know it's the zeros in front, that's perfectly fine. It's okay if you don't know it's interior 0. You're like, it's the zeros that occur in between things. But if it helps you to have a name to memorize it, that's why I tell it to you. I will never ask you, how many interior zeros does this number have? I will ask, how many significant figures? Or maybe identify which zeros are significant and which aren't. But I'm not going to ask for the names like leading and interior. So let's have you practice. How many significant figures are there in these 3 numbers? I'd like you to pause the video and give this a try, and then restart it, and I'll go over it. Okay, so first we have this one here. None of those are zeros, so it's easy. 3 sig figs, 3 numbers. Here, these occur in front of the number. They're leading, they don't count. So just the 2 and the 1 make this 2 significant figures. Here, these are leading, so they don't count. This one, though, occurs between. It's interior. It does count. Therefore, the 4, the 0, and the 2 count. This is 3 significant figures. So the last type of 0 is the one that takes a little more work. This is something called a trailing 0. This one is hard because it depends and it changes. So the first type is if there's no decimal point. If there's no decimal point, it doesn't count. So the number 240 has 2 significant figures. Now, if there is a decimal point, then trailing zeros do count. So 240.0 has 4 significant figures. Because there is a decimal point, all of the trailing zeros count. Not just the ones after the decimal point, but any of the trailing ones. Now, in this third number, we mix together leading and trailing zeros. So there is a decimal point, that means trailing counts. But the first 3 zeros, these right here, these all occur before a non-zero number. Therefore, they are the leading zeros and they don't count. So we don't count these as significant. This number has 3 sig figs, this 1 and these 2 zeros. So that's the last one. So with trailing zeros, if the zeros are on the end, it depends on is there a decimal point. If there isn't, they don't count. If there is, they do count. All of them then, not just the ones after the decimal point, but all of them count if there's a decimal point. So that gets us through all our zeros. And that's all the things where we have numbers by themselves. But we're also going to do math with these sometimes. As you might imagine in a chemistry class, we're going to use equations a lot. You're going to do things like multiply numbers. And we're going to have to keep up with the sig figs, significant figures. We call them sig figs. So when we're multiplying or dividing, the answer should have as many significant figures as the quantity with the least significant figures. So you have to count everything and then only use the one with the least. So, for example, if I have 12 times 24, if I put it in my calculator tells me 288. But 12 and 24 both only have 2 sig figs. Therefore, we would write down 290 because we need to round it. Note, because this 8 is over 5, you should round up. You shouldn't write 280. You should write 290. Similarly, if I take 24 and I divide it by 12, that has 2 significant figures. My calculator only says 2 though. But if I want to report 2 sig figs, I need to report something else. So I put a decimal and I put a 0. Therefore, I can put 2.0. On the other hand, let's say I have the number 123.000. That's 3 trailing zeros that are after a decimal, that are with a decimal point. This thing has 6 significant figures. But I'm multiplying it times 11, and 11 only has 2. So therefore, I'm just going to write the answer 1,400. The idea behind this is we are limited by our weakest measurement. So if we measure one thing super carefully and we're really sloppy with another, the really sloppy one is going to limit us. And so that's what we're going to be reporting, the least number of significant figures. So that's what we do when we are multiplying or dividing. Now, if we are adding or subtracting, the rule is a little bit different. The answer should have as many decimal places as the quantity with the least decimal places. So, for example, if I have 350 plus 12.2, 350, we stop having numbers that were significant at the tens digit. So the tens digit is where I need to round to. In the 12.2, I have something all the way in the tenths digit, so after the decimal point. So when I add that together, my calculator says 362.2. But I'm limited by the number 350. The last significant number there was the 5 and 350. And that is in the tens place. So I write 360. I rounded it to 2 decimal places. Here I take 232 and I subtract 1.1587. Here I'm limited to this 2 in the ones place. Therefore, I put this in my calculator. I end up rounding up my number to 231. Then I have 25 plus 1.0001. So again, this is limited by the ones digit here, so I would put 26. Another example would be if I had 12.5 and I subtracted 1.2015. If I did this, I'm limited here by my tenths digit, so I would get 11.3. Yeah, I can do math in my head. And so I would do it to there. I wouldn't report out all these other decimals because I don't know it as well for the first one. Note that for this class, there are some mathematical reasons of why we use decimal places for addition and subtraction, whereas we use significant figures for multiplication and division. We are not going to discuss that, although I'm willing to if you want to talk during office hours or something, I'm willing to talk about some of the theory behind this, but for the purpose of this class, we're going to be stopping at that. Let's see, do I have, yes, so we have one more. We've got 2 more things on sig figs, that's right. So I'd like you to try practicing these. Pause these, give these a shot, and then I'm going to go over them with you. Okay, so let's start with 250. This is an example from before. Here we've got one trailing 0, but we don't have a decimal place. Therefore, it doesn't count. So we have 2 significant figures. Now here, we have some leading zeros. Those don't count. But these trailing do because there's a decimal point. So we have a total of 4 significant figures. Now here we have an interior 0. Those always count. And we have a trailing 0 with a decimal. So it does count. So I have 1, 2, 3, 4, 5, 6. I have 6 significant figures. Now, we have some calculations to do. So I've got 23 times 0.124. So I do that, and my calculator tells me, let's see, make sure I get this right. Oh yeah, I put that in. My calculator is saying 2.852. But you'll notice we're limited by the ones place there. So when I write that down, I'm going to get all I can write is 3. That's as well as I know the number. That's 2.852 rounded up. Now here I have 134 divided by 2. Again, I'm limited by this ones place. So this is going to be reported as 67. Sorry, 67.0, and I messed this up. Sorry about that. I was doing addition subtraction rules there. I apologize. So that is going to have 2 significant figures. So that will be 2.9. See? It's even possible for me to make mistakes with these 2. This is why, though, it's important that you practice them some so that you will catch your mistakes. And I apologize in advance. I know when the professor makes a mistake, it can be annoying. I will do my best to catch them quickly, though. Now, let's then look at the last ones. So now we're applying the decimal rules. So we have 234.1 plus 1.5, which I put in my calculator incorrectly. So here, my calculator says 235.5, but I'm limited by this digit here. So this is going to be 236. So I have to round up. Now here I have 12.4 minus 1.26. So here we're limited by the tens digit. So when my calculator says 11.14, I'm going to write that down as 11.1. That's what I know. So make sure to practice ones like this. If this gave you some trouble, there are additional problems recommended on the practice guide. So on the study guide review sheet I've got that you'll see with the chapter notes, it's on Coursden. You can look at that and you can do some more practice problems. If you are viewing this and you're not in my class, I recommend you can Google, there are lots of significant figure practice problems. They're very helpful. These are one of those things where if you practice, they get pretty easy. Like some problems, they don't change quite as much, I find, but significant figures, I found for many students, they get pretty easy if you just do a number of them. Once you sort of get the rules down, they can become second nature. But at first, they feel a little challenging because they just feel kind of weird. They're like, why are these rules here? But as you internalize them, they get pretty comfortable, I find, for most people. Now, we have a little bit more conceptually to mention. So if you have exact numbers, we're going to treat them as having infinite significant figures. So let's say you have 1 apple. That means you have exactly an apple. You didn't measure it with a ruler. You're not like, oh, is there a 20th of an apple hiding somewhere? You have exactly 1 apple. Therefore, we can use as many decimals as we want. It's going to be other measurements that limit our significant figures. We're also going to treat conversion factors as exact numbers and treat them as having infinite significant figures. So 100 centimeters equals 1 meter is a definition. It is exactly true. There are always 100 centimeters in 1 meter. You're not going to find out there's actually 99.999 centimeters in 1 meter. It is always exactly 100 centimeters equals a meter. This becomes important because we start multiplying by these conversion factors later. In our multiplication rules, you might assume, oh, I only have 1 meter. I only have 1 sig fig. I better reduce that down. So you will not have to worry about the conversion factor portions because we're going to treat those as being exact numbers. They're not going to make us reduce our sig figs. You'll also notice that sometimes you have answers that you can't write correctly with the right number of sig figs if you try to write them normally. Well, I don't want to say normal because scientific notation is normal too. But if you try to write them without using scientific notation, you have a problem. So for example, you take the number 1600, you divide it by 2. If you do that, your calculator is going to tell you 800. But this has 2 sig figs, and this has 2 sig figs. 800 can't be written with 2 sig figs like that. So we convert it to scientific notation, where we have 8.0 times 10 to the second. And that's because I took my understood decimal that you don't see, and I moved it twice. That makes the number. And so I moved it twice, that's 10 to the second. And then it's 8.0, so I have 2 sig figs. If I wrote 8.00, that would be 3 sig figs. And so you can convert any number by doing this. So for example, the number 0.00450, I can move the decimal 3 times. And this time I'm moving it to the right. So I'm going to multiply by 10 to the negative 3. So I have 4.50 times 10 to the negative 3 is a scientific notation way to write 3 sig figs. Do note that 0.00450 would also have been an acceptable answer for a problem with 3 sig figs. It's correct. I just also want to show you, you could always write it in scientific notation. That always goes fine. So that ends our work on significant figures. You will be using these though. So we'll have some specific questions where we go, how many sig figs is this? But you're also expected to keep up with this when we do problems in the future. So you do a conversion factor problem, you need to make sure you report at the end the right number of sig figs. So you'll keep applying these rules throughout the entire semester.